So 5 years ago, when I started my PhD, I was very motivated and excited to do research in optimization, partly because historically optimization research has been very influential in practice. Oftentimes it leads to very disciplined and reliable applications. So what I mean by that is solid theoretical research in optimization has led to many applications. One of my favorite applications is something called compressed sensing, mostly done by Caltech and Stanford back in the days. They just pure mathematics developed some technology which is applied to MRI technology and leading to a lot of speed up. Now we can just do MRI really fast. Apart from that, you want to go somewhere, map navigation, which is purely optimization. A lot of my office mates work on power system management. It's also optimization. And let's say you go back home and start watching something on, Netflix, whatever, movie recommendation, content recommendation, song recommendation, everything is optimization. And what I like to emphasize here is that all these applications are very disciplined. Like strict theory, strong theory actually leads to these applications. All right, fast forward to today. We cannot talk about optimization without talking about AI, machine learning, right? We see all these giant, large models appearing, every month, every day. So large AI models, very important application of optimization, large language models. But I would like to make a claim here that these applications are quite different than previous applications in the sense that we don't really understand what's going on. Okay? To give you some evidence, these models are trained with lots of heuristics. AI engineers somehow figure out the way to train the model. And consequently, there are a lot of hyperparameters to tune. And you guys might have heard that like in AI, there's like reproducibility crisis. Some like startup came up with nice model, and later on, people cannot reproduce it even because there's so many hyperparameters, a lot of heuristics. Another evidence is it takes a lot of computation power and substantial costs to train large models. And we don't even know whether this is the optimal way to train all these models, just because we don't know what's going on. Okay? So here's my pitch, or the ultimate goal of my research life. Can we understand training large AI model, optimization in the large model era, and try to guide practice? Okay? These are very grand questions, billion-dollar question, but obvious challenge here is that models have so many parameters on the order of billions. Yeah, it's very scary. Specifically, it has led to, in recent days, lots of new phenomena that we cannot understand from the view of traditional optimization ideas. Okay. So in order to talk about what I mean by new, I first need to briefly introduce how AI models are trained. Basically, without going into details, data, lots of data and huge model with lots of parameter gives you something called training loss. And the name of the game is just optimize this training loss as much as you can, as fast as you can, to figure out the configuration of the parameter, the optimal parameter that achieves the lowest training loss. So that's basically how AI models are trained. You just try to figure out the optimal configuration of parameters that achieves the lowest training loss that's built upon data and model. Okay. So given this pipeline, what I mean by new is, in recent days, we have seen new algorithms train AI models, and even the training dynamics themselves show new phenomena. And what's more is a train model, the resulting optimal configuration of parameter, also shows some new phenomena. So these are some vague words, and in the next couple of slides, I'm going to show you what I mean by this. First, in order to talk about what's new, I guess, just to be on the same page, I'll have to talk about old ideas. Okay. So this is the pipeline, and throughout the thesis, we're going to focus on the second half optimization part. We have the training loss constructed by data model, and we want to just get the lowest training loss as fast as you can. All right, so a little bit of math here. So F, let's say, is the training loss function that maps from the number of parameter, R to the D dimensional Euclidean space, to some scalar. Okay? And you want to make this training loss as low as you can. So figure out the X star in the Euclidean space that achieves the lowest training loss. And traditionally, it's very well studied, just training or optimization, very well studied when F is convex or convex-like. What I mean by that is the training loss function landscape looks like this, just like a single Bayesian. In this case, intuitively, you can just identify where the lowest point lies in. It's just like the bottom of the Bayesian, right? So it's like intuitively kind of easy to optimize this kind of convex function. So let's say you're at the top of the mountain and you want to reach the bottom of the mountain. And what you got to do is just follow down the downhill, right? Then you will reach down the lowest point. And that's basically the idea of the mother of algorithm gradient descent, where you start from the initial rate and keep following the downhill. Mathematically speaking, it's like at your current iterate xt, you compute the gradient, and gradient is the direction along the loss increases. So you follow the negative direction of the gradient, and you keep doing that iteratively, and you'll reach down the bottom of the Bayesian, which is like the optimum configuration of the parameters. Okay. All right, then I'll start talking about what's new, what's happening in the large model training. Turns out training losses of large AI models are highly non-convex, and I'm going to show you some nice visualization from recent works. This is ResNet training loss landscape and this is another training loss landscape of a large model. As you can see, these are far from being convex. And if you're thinking about just going down the hill, that kind of intuition doesn't apply here, right? And also, like, I like to highlight that this is just like 2D, projection of the landscape, and the actual dimension is R to the D, where D is like on the order of billions, right? So at that point, yeah, it's hard to think about how optimization works, right? And on top of that, what I didn't talk about is the training loss function is built on top of data, and in order to compute this exact gradient, you have to go through all the data, so which is impossible. So oftentimes people approximate the gradient with something called stochastic. So now you don't have the exact direction where the loss is decreasing, so you only have the approximation on top of that. Landscape is very crazy. So you cannot apply the just go down the hill intuition anymore. So, but then we have ChatGPT, all these like large foundation models. How are they trained? Basically, over the years, a lot of AI engineers just made it work with a lot of heuristics. They develop new algorithms, and somehow it works. Sometimes it cannot be reproduced, but they somehow figure out the right parameter to optimize and so on. So I'm going to talk about in the next few slides the new phenomena in large AI models optimization. First thing is the training requires new algorithm.
Yeah, I've sent it. I'll book in due course. Anything else?
I'm sorry.
I'll book in due course. Anything else?
All right. So traditionally, like I said, people use stochastic gradient descent. Train AI, like machine learning models, but then for training large models, these mother of algorithms don't quite work anymore. It turns out there's a new algorithm called Adam, developed in 2014, that works much better, and it's actually the default choice. If you talk to any AI engineers, nobody would train their models with SGD gradient descent. They'll just by default use Adam. Okay? What is Adam? I'm going to talk about it like later on, more details, but it actually for AI people, it's algorithm that needs no introduction. It was just less than 10 years ago, and it got cited more than 80K times already. Yeah, literally in AI, everybody knows Adam. It's very extreme popular. Yeah, everybody uses it. And let me just show you some plots to show you effectiveness of Adam for training large language models. So when you train like transform models for language modeling tests, and what I'm showing you here is a plot of the training loss curve over the number of iteration of the optimization, and the black curve is SGD, and the red curve is Adam. And name of the game here is, can you reach down the loss? Can you reduce the loss as fast as you can? And you can see that there's obvious performance gap between Adam and SGD. And what's more interesting is perhaps the fact that for those who took the machine learning 101 or computer vision class, we always love to train like smaller size convolutional neural networks for image classification. For those kind of smaller scale setting, turns out there's no gap between SGD and Atom. This is actually adding more interesting aspect to this phenomena. It seems like it's actually happening for the larger scale or this large language model based models. Actually, it was reported in one of my committee, Asia Wilson's paper back in 2017. And like I said, training dynamics themselves show new phenomena. This part will be a little bit more technical. So I told you that you cannot compute the exact gradient, you compute the stochastic gradient, and for the stochastic optimization to work, the standard assumption is that stochastic gradients are behaving well. In mathematically speaking, that's the bounded variance condition where difference between, roughly speaking, stochastic gradient and full gradient is nicely bounded in expectation. That way, stochastic gradient is kind of like a good estimate of the real gradient. But the recent works, including my previous colleague, Subritz and Ali's ex-student, Jing Zhao, they plotted the histogram of stochastic gradient noise along the training dynamics and noticed that for large model training, it's much more heavy tail than the smaller size training. So what this is indicating is that standard assumption for SGD, stochastic optimization to work, breaks for large language model training. It's heavy tail. You cannot do this bounded variance assumption anymore. It's again, like I said, it was reported in Jing Zhao, Zhang, our Subrit and Ali's ex-student and my advisor back in 2020. Lastly, this is not it. Optimization showing new phenomena, new algorithm.
But if you still think stuff,
Train model themselves show new phenomena. And one prominent example is something called in-context learning. And without giving you a formal definition, a nice way to describe this is just give you an example. Let's say we need to come up with a Spanish to English translation here, right? Then all you have to do is just go to your favorite language models, and in the prompt input, you just give a couple examples of the task you want to solve. Just couple pair of Spanish to English translation and new query here, in this case, Pero, and then output language model during its inference for pass will just automatically recognize the task and just solve it for you. Okay? First, it was kind of like coined in this GPT-3 paper from OpenAI in 2020. And it has led to a lot of interesting application, and it's been regarded as one of the nicest property of like language models these days. Very exciting topic these days. Just because I'll give you a little bit more background, before in-context learning, the way you apply your trained model for downstream application is you take your model and do a further optimization process called fine-tuning optimization, where you change the weight of your trained model a little bit more toward the downstream application so that your model adapts to the downstream application. But what this in-context learning is saying is you don't need any of that. Just in your input or prompt, just give a couple examples of the task you want to solve, and language model will just do it for you. So it has led to a lot of interesting application. Okay, so with these 3 slides, the point I'm trying to make is there are lots of new phenomena that we don't understand in the large model era. So where do we go from there? I guess the obvious question is, can we first at least understand these individual aspects to gain the insights and move forward, right? So that has been like focus on my thesis. But again, the challenge here is that, look, the D is on the order of billion. Like what can we do with this huge system, right? So I took 2 approaches in this thesis. The recurring theme in my thesis is first, I rely on simple models and control experiments inspired by science. You know, when I look at my friends in working physics, mechanical engineering, chemistry, they're dealing with also very complex system, you know, thermodynamics and so on. Yet they have been really successful in like predicting what's going to happen in the future based on like the simple models and controlled experiments, right? So why don't we just get inspiration from there, and we also do the similar thing for AI? Right? So I'm going to use the simple models to capture the essence of the phenomena and also gain generalizable insights. Another thing that I use for mostly understanding new algorithm is something called practical formalism. So I define the right notion of performance metric under which I can show the advantages of the practical algorithms, hence developing practical theory that's reflective of practical application. Okay, so these like description look a little bit more vague at this point, but I'm going to give you several examples throughout the this talk, and hopefully by the end you'll have a better idea of how I've been using these approaches in my thesis.
Very quickly, that should be X double dot.
Oh yes, thank you. So my thesis consists of 3 parts. Part 1 is understanding new phenomena for large language model that I described earlier. I'm going to use a simple models because transformer, these large language models are so complex. So I'm going to rely on simple models and control experiments to kind of understand what's going on here based on 2 works. One about in-context learning, joint work with Xiang, Hadi, and Subri, my advisor, appeared in Europe last year. And then I'll also talk about difficulties of transformer training. Again, joint work with Xiang, Minak Song, Shari Yun, Ali Zabab, and Subrisra, both my advisors. And then after that, I'm going to talk about second part of the thesis, which is about Adam, that algorithm that I talked about, understanding Adam, based on practical formalism. And I'll talk about 2 works here. New perspective on Adam. It's a joint work with Ziyu from Harvard there, and Yunbum and Yan. It's going to be presenting ICML Austria this year. And theoretical guarantees for Adam, which I just wrapped up with Ashok Kokoski from Boston University. And unfortunately, I won't have time to cover one of my favorite parts in the thesis, which is unstable training and flat minima part, based on really nice work that I've done with my collaborators, Jing Zhao, my advisors, and some people from Microsoft, Sebastian Sinho, Inta Lee, Felipe Suarez, Izang, and work that I did and going to be presented in ICML this year with my 2 advisors about flat minima. So those who are intrigued by the topic, title, please come talk to me or refer to my thesis. All right, so let's dive right into the part 1 of the thesis, which is understanding new phenomena for large language models. And I just have to say, by large language models, it's actually transformers. Is it this transformer? Unfortunately not. It's actually the transformer from this famous paper, Attention is All You Need, from Google back in 2017, which coined the term transformer. Transformer is the neural architecture that's it's a building block for the large language models. So basically, I'll just use LLMs, transformers, synonymously throughout the presentation. We'll focus on understanding in-context learning for transformer-based models and main difficulties of training transformers. Okay. So in context learning, I told you about the Spanish to English translation, this remarkable property of large language models. So the question here is, what mechanism do trained transformers use to achieve this remarkable property? The challenge, obviously, is that in context learning is observed for large models, and fully fledged transformer has this very complicated architectural structure. So it will be kind of quite difficult for us to do any theoretical investigation if architecture is so complex like this. So like I alluded earlier, we're going to use a simple model approach and also rely on very simple task, statistics 101 linear regression task. Okay, so the setting is the following. We're going to try to solve linear regression in context. So say yi, the scalar, is a dot product of xi with the ground truth W star. So same vein as the in-context learning, we're going to give a couple examples of xi, yi pair, linear regression, and ask a new xn plus 1 and have the language model to predict yn plus 1. Okay? So language model has to figure out this ground truth W star to be able to answer this question, linear regression question. So how transformer solve this task? We theoretically study based on simple toy transformers. So this fully fledged transformer is kind of cumbersome to do a theoretical analysis, so we're gonna dumb it down to toy transformer. So I didn't really talk about what transformers are, and for the purpose of my talk, we don't really have to talk about the definition of transformer, but those who are expert in the audience who know transformer, the architecture I use is basically fully fledged transformer. You would use multi-headed attention, but we're gonna use a single head linear attention and just repeat them for L times, where L is the number of layers. This is a lot simpler than the fully fledged transformers. And the training loss is nothing but the square loss on the random instances of this linear regression in context. So that's the training loss. And it's a non-convex training loss. So I'm going to talk about the main results at a high level first, and then formally later, okay? So, toy transformer, trained toy transformer does the following for the in-context learning, okay? So it might sound a little tricky at first, but I'm going to break it down further later. So it sets up its own machine learning problem, hypothetical training loss, least square problem based on xi, yi pairs given in the prompt, and set up its own training loss like this. And you will just solve it with its own hypothetical optimization algorithm to get to output W hat, and use this W hat to predict the query xn plus 1, y hat n plus 1, okay? So what I'm trying to say here is that toy transformer, which is trained based on this training loss, itself is doing a little small AI optimization in itself. So it sets up its own training loss based on xi, yi, and then it somehow implements some gradient-based optimization, the gradient descent, let's say, to solve it and get the answer and use that to do a prediction. It's a kind of like doing a small AI within larger AI, kind of like a meta interpretation. So formal results are like this. So what we did was carefully analyze a non-convex training loss landscape for this case and show that, let's say, L is the number of layers in transformer architecture, toy transformer architecture, and T is the number of steps of the optimization algorithm the transformer is implementing. And we show that L is equal to T. So basically, theorem says trained toy L layer transformer corresponds to implementing L steps of gradient descent, mathematically the stationary points of the training loss. So, and whenever we actually experimentally train this toy transformer, it always converges to stationary points. So we conjecture that these stationary points are actually global minimizer or local minimizer. And we actually were able to show that for single layer case, show that it's actually global minimizer. All right. And some optimization experts in the room, the optimization algorithm that it implements is not just gradient descent, but preconditioned gradient descent, more advanced gradient descent that leads to faster optimization. So, which is kind of interesting. Transformer is doing something more than gradient descent. So takeaway so far here is that simple models can give insights about this very practical phenomena in context learning. But at this point, maybe you dumb down the transformer too much. Like, how is it gonna make sense? Actually, it turns out many empirical results for fully fledged transformer match our theory. They said that it's actually setting up some hypothetical loss function and implement some hypothetical gradient-based optimizer to optimize it and get the answer to in-context learning. So in this case, toy transformer is a good representation of the fully fledged transformers. I just want to highlight lastly that our work, the simple model-based approach, inspired lots of follow works in the literature regarding other in-context learning aspects. Okay, so let me move on to the second paper. I'll talk about second example, try to understand main difficulties of training transformer training. Transformer training, as I said earlier, requires lots of heuristics. It's known to be very difficult. And recent works have identified several unique features about transformer training that might have caused these unique difficulties. So I already showed you during the introductory slides two features. It requires new algorithm like Adam, and it shows new training dynamics like heavy-tailed stochastic gradient. Right? I just want to point out here that these identifying new features of transformer training is actively studied research in the literature. There are other features, but I won't have time to go over them in detail. But the main takeaway here is that recent works have identified several different features of transformer training that might have caused its difficulties. But again, understanding them is hard because it's observed for large models, and the features they observed seem quite distinctive. So can we come up with one simple model that capture all these? Was a research question that I asked in this work, and our main result said yes. So the simple toy transformer training I just discussed for the first paper, that exact setting reproduces all this feature, is a main result in our iClear paper this year. So I show you that there's a gap between Atom and SGD. We exactly reproduces that feature with this very toy transformer training. It's like very simple that you can even train on your CPU within like 10, 15 minutes. Our models are really simple like that. These pre-training takes like weeks to get this plot. For the heavy tail stochastic gradient noise, the new training dynamics phenomena, we also exactly reproduce this with our simple toy transformers. And for the interest of time, I won't be able to show you this parallel plots for feature 3 and 4, but we're able to capture all these features with just one simple toy model. Yeah, so again, fortunately, we're able to capture fully fledged transformer with a simple transformer. And obviously, the main advantage here is that it's simple and concrete. We can do lots of interesting theoretical analysis because architectures are simpler. We already did some landscape analysis in our in-context learning paper. Also, we did some control experiments in our paper just because architecture is simple. We can change like the several variables in the architecture to see what happens. So basically what we did was 2 different control experiments where we change the data distribution to be more complex or just increase the number of layers to make the architecture more complex. And we consistently observe that the unique features that we observe becomes more pronounced as we either make the model complex or the data more complex. Okay. So we're reaching the end of the part 1 of my thesis. So simple models and right control experiments can share new insights about the practical phenomena and understanding practical mechanisms like in context learning. And we hope that it will serve as good models for future theory for us to understand what's going on in the large model. Okay. With this, let me move on to the second part of the thesis. And a little bit introduction here is that we just saw that Atom is very effective. It's the default choice for training large models. I show you that it needs no introduction. Everybody knows, has been cited a lot of times. So the question is, can we understand why Atom is so effective? Okay. An Atom optimizer, it's a coordinate-wise algorithm. So it's coordinate-wise. Since it's coordinate-wise, I'm going to use a scalar xt/gt applied to each coordinate separately instead of the bold font xt/gt vector notation. So for SGD, it's doing something like this. Like I said, at your current iterate, you move toward the negative direction of your stochastic gradient each time. It's like following the downhill idea. But what Atom does is quite complicated. Bear with me. It chooses this discounting factors and choose this non-trivial combination of stochastic gradients observed so far and take the fraction. So yeah, this is why people couldn't understand why Atom worked. Just by definition, it's just very complex looking. So the key component here, let me break down a little bit. It uses, so SGD uses this just last stochastic gradient, GT, while it will keep track of all the stochastic gradients observed so far. And this feature is called the momentum in the literature. With the discounting factors beta 1, beta 2, it's keeping track of this exponential moving average, discounted average of the stochastic gradient observed so far, and discounted average of the square of the stochastic gradients observed so far, and take the fraction. Okay. So we saw that Atom is doing this crazy operation for optimization. then what do we understand about Adam? Like I said, it's a very popular algorithm. A lot of nice works have come up with a theoretical analysis of Adam. But I'd like to make a point here that our current understanding of Adam remains incomplete, mostly because most existing works consider either convex or smooth training loss function setting, for which, unfortunately, methods like SGD already achieves a theoretically optimal convergence rate. So in other words, under these settings, we don't really have room for us to show that Adam is better than SGD because SGD is already achieving the optimal. In fact, the two latest work both mentioned that the results get worse with momentum, meaning if you turn off the momentum, you will get better convergence rate, which is not the case. If you turn off the momentum, you cannot train the neural networks. And the rates for Adam is no better than that of SGD, which is not what we saw in the plots even that I showed earlier. Adam is noticeably better than SGD. So far, I would like to make a claim that theory about Adam is not reflective of practice. So is there a practical theory for Adam that underscores the key components like momentum and discounting factors? And obviously, you need to step away from the conventional analysis of Adam. So that's going to be scope of the part two. I'm going to talk about two works. One about new perspective on Adam, joint work with Ziyu sitting at the back from Harvard, Yunbom and Yan. And then another work about theoretical guarantees for Adam, joint work with Ashok Koski from Boston University. So whenever you have like this complex objects lying around, for me, a better way to understand is let's abstract things a little bit away. So let's consider this like generic optimization scheme where at your current rate, somehow you do whatever, come up with the delta t is the update direction, and you move toward that. Okay? So stochastic gradient descent will choose delta t to be minus the negative direction of the current stochastic gradient, right? And Adam does this fraction thing. Right. So name of the game here is that given the observed stochastic gradient so far, G0 up to GT, what would you choose for new update direction, delta t? Okay. This is kind of like a sequential decision making where you make a decision and the environment reveals to you additional information, GT, and then you combine that to come up with a new decision, and the environment reveals to you another information about the environment. So this is kind of like sequential decision making, like kind of game kind of setup. Fortunately to us, it's very well studied in the literature in the machine learning community known as online learning. There are already 3 nice textbooks on this, actually more than 3, just giving you some example. I'm just showing you that it's very well studied in this field. So the main idea in the new perspective on the Adam part is that why don't we just use, like online learning is a rich literature. They have developed dozens of algorithms that achieves like a good performance. Why don't we just take one of those and apply it to delta t and see what happens? Okay. So in this way, you can just take online learning algorithm and use that to design an optimization algorithm. So the main result in this new perspective paper is that I just show you that you take online learner of your choice and it turns that into optimization algorithm. And it turns out Adam just corresponds to very famous online learner called follow the regularized leader, FTRL, which is very nice. It's if you open up one of the textbook that I just mentioned in the previous slide, second chapter, it's follow the regularized leader. So it's adaptive online learner, which is known to be very good. On the other hand, SGD corresponds to poor online learner under this reduction. So I can tell you without going into any math why it's the case. Right. So look at this. Adam carefully does some combination of all the past history gradients. And this is actually corresponds to some variants of FTRL. But when you look at SGD, environment has revealed to you T+1 information about the environment. And you're just ignoring G0 to GT-1. And I'm going to just use GT to make the decision. Right? This is definitely suboptimal, right? And this is kind of like a key idea behind our analysis, showing why this online learner is poor. Yeah, it's in some sense doing this poor decision making. Why would you ignore all the information that's given to you by environment? Okay? So theorem informally says that if you turn up momentum, so if you don't combine the stochastic gradients observed so far, or if you don't add discounting factor, the online learner becomes poor and then leads to poor optimization algorithm. Hence, you can kind of understand why Adam is more successful than SGD. It's using a lot more online learner that's a lot more sensical. And for experts in the audience, what I mean by poor is it will achieve poor dynamic regret, one of the performance metric in the online learning. So a new perspective on Adam's, it gives a new perspective on Adam's algorithmic components. Now you can understand why momentum is important and discounting factors are important. Really quickly, in my recent follow work, building on this perspective, we actually was able to come up with a nice concrete theoretical guarantee saying Adam with model EMA, exponential moving average, I'll talk about that in a second, achieves the optimal convergence rate for non-convex optimization, both for smooth and non-smooth settings. And especially this coordinate-wise adaptivity of Adam shines when the scale of coordinates varies a lot across different coordinates. So model EMA, again, as much as Adam, it's a very popular technique. Those who have talked with any people who've been training high quality diffusion models, image generating diffusion models, they would just use model exponential moving average by default. Otherwise, training becomes too, training dynamics becomes too complex and you wouldn't get like a high quality image generated model. So it's very nice that Adam with the model EMA is what people would use to train large models, diffusion models, or even language models. And it's not really nice that theoretical optimal algorithm is what people use in practice. Just to give you context in optimization, machine learning optimization theory, it has been like, for example, I mentioned that SGD achieves the optimal rate for the smooth or convex setting, which is not reflective of practice, but these result is at least reflective of practice, which is really nice. And in our analysis, we heavily use on Adam and EMA. So it's shedding new lights on the roles of these algorithmic components. All right, so I'm done with the two parts that I want to talk about in my thesis. And to sum up, large models have billions of parameters, and I was able to make some progress toward understanding large model optimization based on simple model approach and practical formalism. Okay. So a quick remark about what's next. Definitely, I'm going to continue working on understanding AI optimization, understanding how large AI models work, how to do training more efficiently, and so on. But I guess for me personally, over the last years, I was working more on the science aspect of AI, and moving forward, I would like to work on also like the societal, like technology I'm developing. What's the societal impact of this technology? Also, maybe since I've been always working on like my personal projects moving forward, I'd love to figure out ways to contribute to the society with my expertise. I'll give you a little shout out to all my collaborators. Without those collaborations, I don't think I could have come up with this thesis. Obviously, Ali, my advisor, and Subrit's group taught me a lot about optimization, control, reinforcement learning, transformers, leading to solid parts of the thesis. And also Professor Philip Rigolet's group. I was learning a lot from them during my second and third year about sampling and optimization. I spent 2 summers at Google Research working on interesting problems regarding reproducibility, robustness, and accelerating language models. Professor Navid Azizan's group, I was able to work on some interesting problem regarding implicit bias and continual learning. Microsoft Research, I had a collaboration there. That's where I started thinking about the simple models approach more seriously. And lastly, recent collaboration that I did with Ashok Kakasi at BU, and Ziyu from Harvard. They taught me a lot about online learning that led me to do all this interesting work regarding Atom. Last but not least, I would like to thank all the MIT gymnastics member. Thank you for coming to the thesis, and doing gymnastics, has been really, it just kept me kept me in check, and I was able to just keep my sanity with gymnastics, training gymnastics. Thank you all. All right, so thank you for listening. I'll conclude here, and I'll take any questions.